My name is Ms. Cummings, for those of you who do not know me or who log into Zoom, be counted present, and then walk away from their computers and therefore have never seen me before. So I'm going to be doing a really quick video going through all of the units we've learned this semester. I'm going to try to keep it under 15 minutes. That's 5 units. So I'm going to be talking really fast, spit a bunch of facts at you. I got notes right here, so I'll be looking at those. If you need to slow me down, you can use the settings in YouTube and slow down the speed that I'm talking. Okay, so I'm going to get started. All right, so Unit 1. So you want to remember that everything is made out of atoms, and everything made up of atoms takes up space and has mass. Atoms are really small. You have to use an electron microscope to see them. You can't see them with a regular microscope. You can see cells, but that's a level up of organization, levels of organization. Atoms are made out of protons, neutrons, and electrons. Remember that protons and neutrons have a mass that we count. It's about 1, and electrons have a negligible mass. So remember Bohr models? Remember when we were making Bohr models? You put the nucleus in the middle, which is the protons and the neutrons, and then you put the electrons in outer rings. So when we're talking about Bohr models, the rings are going to be, the first ring is going to be 2 electrons, second ring is going to be 8, third is 18, 4, 5, 6, and 7 are 32. The electrons on the outside are called valence electrons. Those are the ones that are, making bonds, making, elements have their properties, things like that. The amount of protons, neutrons, and electrons is going to, make the element. It's going to make it what it is. Let me see. This is what I want. So when we're looking at the periodic table, if you're looking at, say, carbon in this instance, the top number is going to be the atomic number. That's the number of protons. So it's always going to be 6 protons for carbon. It's always going to be the same amount of protons. If the amount of protons changes, the element has changed. Okay. The symbol is in the middle. It's the letters. It stands for whatever element we're talking about. Doesn't always, it's not always an abbreviation of the name. And the bottom is going to be the atomic mass. Remember, we only count protons and neutrons in mass. So it's protons plus neutrons equals atomic mass. And when we're not talking about ions, the amount of electrons is going to equal the amount of protons. So in this case, we know we have 6 electrons for carbon if we're not looking at an ion of some sort. So you should be able to look at the periodic table and see, point out the atomic mass and know the amount of protons and neutrons from looking at that, and electrons of non-ions. Is there anything else I wanted to say about this? Keep going. So I already talked about Bohr model. Okay, kinetic molecular theory. Okay, so we're going to be talking about phases of matter with kinetic molecular theory. So basically, particles are always in motion, right? Now, the amount of motion is what is going to make whatever phase they're in have its properties. So solids, remember we have some small vibration of particles. They are tightly packed together. But remember, solids have a definite shape. This is a solid. It has a definite shape. It's not going to change unless I crush it, but that's different. It has a definite volume that doesn't change. The particles don't really flow. They're just kind of there in their space, and it cannot be compressed. Like I can't just change this and it'd still be a mouse. Okay. Liquids. So liquids are kind of moving past each other a little more. We have a little more movement happening. They have an indefinite shape. I can, put this in another container and it would take a different shape. However, they do have a definite volume, and it can be compressed. Gas particles, they're going all over the place, right? Moving really quickly. They have a lot more kinetic energy. It has an indefinite shape. It just, gas particles are all in the room around you. Indefinite volume, because they're so far spread apart. The particles are moving and they can be compressed. I can take a certain amount of air and compress those air molecules closer together. Okay, so when we're adding energy or, adding temperature to a state of matter, it's going to change phases. So the more, the higher the temperature it has, the more kinetic energy it has, and therefore the more movement of particles. And so we get closer to gases as we go, as we add kinetic energy from solid to gas. Okay, so you want to be familiar with this graph. Remember kind of what's happening. We have going from a solid to a liquid. We have melting during this flat line here, right? From water to steam, we have boiling, and then we also have the processes as we come down, which is going to be condensation from gas to a liquid and freezing from a liquid to a solid. Think about water. You know all those things. You've learned the water cycle, right? We're good. Okay, moving on. Unit 2. I think I want this. Nope, I want this one first. Okay. Unit 2. Okay, so like I said, elements. They are a pure substance made out of just one type of atom. If we have multiple types of atoms, we're talking about compounds, which we got into kind of towards the end of the semester, right? So these atoms, to make elements, are held together by attractive forces. The closer we get from, like, if we're looking at a scale from solid to gases have weaker attractive forces, right? Solids have the stronger attractive forces. That's why they stay solid. Okay. Okay. So we need to talk about electrons. So like I said, valence electrons are really the key to what makes an element and what makes certain things combine the way that they do, things like that. Kind of the whole, the theme of this semester. Okay, so remember metallic bonding, that the electrons are kind of free. They're in a sea, they're moving around. So they're moving around those positive nuclei of the metal atoms, and so it keeps it together, but it also gives it specific properties. So they're all kind of sharing those electrons. The electrons can move around. That makes it a good conductor of both electricity and heat. It also makes them malleable and ductile. Remember, malleable is able to move. Ductile, we can turn it into wires and it's still the same, material. Metallic bonds make things have a lower melting point. So they're going to melt easier than say our covalent bonds. The bonds will break easier. Yep. Okay, network solids. What I really mean when we talk about network solids is covalent bonding. So remember the electrons, I said they were kind of holding hands. So we have electrons from, two different atoms, and they're joining together to form a bond. They're going to be more of a lattice structure, and they're going to have higher melting points because those bonds are stronger than just the kind of loose electrons, right? They're not really conductors because they don't have, moving electrons. They're stuck in place. They're going to be hard, brittle, and dull. Okay, physical properties. I already kind of went over that. Remember that density equals mass divided by volume. Malleable and ductile, I said those, so the nuclei can kind of slide past each other because those electrons are still keeping them together. Color is reflection and absorption of light. So remember that, excited electrons move and then they emit like a wave, and that wave is whatever color that we're seeing. And everything like this mouse, well, I guess pink's not good, is basically absorbing pretty much every color except for like reddish. Talked about luster. Density equals mass divided by volume. Remember that. Talked about conductivity. So remember heat, electricity, and sound can move through substances, and they can move through metals best. We know about melting point and boiling point. Okay, specific heat is kind of the last thing I wanted to say. Okay, so remember specific heat is the capability of a material to hold heat is heat capacity, and then specific heat is a measure of heat capacity. So how much heat do we need to raise the temperature of 1 gram of substance by 1 degree Celsius? So how easy is it for something to heat up, right? The more tightly packed particles are, the easier it is the easier it's going to be to heat the particles. When things are more spread apart, it takes longer to get heat through the substance. Okay, so remember that structure and bonding kind of gives you the properties of an element. I'm sorry. Okay, moving on to the periodic table. This is still unit 2, I believe. For minutes. Okay. Periodic table. So we have group 1. That would be the alkali metals. They are highly reactive. They have 1 valence electron, and they want to get rid of it. Remember, we want to meet the octet rule. So if we just have a couple stray electrons in the outer valence shell, they want to go bye-bye. So they're going to try to get rid of them. Okay, group 2, alkali earth metals. So they form ionic compounds really easily, and they have 2 valence electrons. Okay, in the middle, groups 3 through 12 is going to be transition metals. They have pretty much the properties of metals that I was talking about earlier. So pretty hard. They're malleable, they're ductile, they conduct well. Halogens. So we're skipping all the way over to group 17. Then we're going to come back. So halogens, second to last group. Remember, halogens means salt making. So they have 7 valence electrons. And if they want to meet the octet rule, they're going to take 1 valence electron, probably from alkali metals in group 1. Right? Super easy kind of mix. Group 1 wants to give away its 1 electron. Group 17 wants to take 1 electron. So it's match made in heaven. Okay. So those are going to be pretty reactive. And then the least reactive group, the most stable group, is going to be the noble gases. That's group 18. And group 18 has a full valence shell, so they kind of want to stay where they're at. And they're all gases at room temperature, but they're pretty non-reactive. Okay. Now remember, I want to kind of give you guys the trick in case you forgot. When we're looking at valence electrons, don't look at these low groups, but if you count across the top, the taller groups, you'll know how many valence electrons each element in that group has. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Okay. Now we're going to talk about metalloids. So they're kind of like metals, kind of like non-metals. Kind of just depends on what's happening in the reaction, what reactions we have with it, and they make good semiconductors. That means they're kind of on conducting, not amazing, but not terrible. So that's kind of the staircase-ish. Well, not staircase, but you get my drift. And then underneath that, we have more metals. So pretty much same kind of deal as the rest. Okay, non-metals. Here we go. So they're going to be poor conductors. They're going to be brittle solids. They don't really have any luster or shine. They gain electrons really easily. They're going to be more likely to be bound to each other, kind of have more covalent bonds, things like that. Moving on to Unit 3. Let's do it. Unit 3, super easy, okay? You just have to remember what fission is and what fusion is, okay? So remember in fission, we throw like a neutron at an atom to split it. And when we split that, it's releasing a lot of radiation, or, well, yeah, it is releasing radiation. It's releasing some other neutrons, and it's also releasing a ton of energy, okay? So fission causes radiation, releases lots of energy. It's what we use for nuclear power. It's what's used in nuclear bombs, because those neutrons, if we don't control the reaction, those neutrons will go and split other atoms, and it just causes a chain reaction. That's why we have power plants with all the controllers and things like that, moderators that keep the reaction in check so we don't have a bunch of stray neutrons going around blowing things up. Okay? So that's fission. Now fusion, I want you to think about fusing things together. So like a welder fusing two pieces of metal together, we're throwing isotopes of hydrogen at each other at high velocities and high temperatures in order to make energy. Okay, I'm gonna skip all this stuff. That is fusion. We're basically fusing, we're causing two atoms to fuse together. It requires a ton of, like, a really high temperature. The atoms have to be moving very quickly. It happens naturally in the core of the sun because of the temperature and just how, like, pressurized it is, right? Makes so much energy, more than fission. But because of the whole process, it's kind of hard to keep going without a super high temperature. So we can't use it for clean power because this doesn't cause radiation. Can't really use it for clean power because of how much energy input it requires to keep the reaction going. They're working on it. We'll see if it happens one day, but unlikely. So fission, breaking, fusion, putting together. Okay, both cause energy. Fission is the one that we use here on Earth. Okay, moving on to Unit 4. We're almost done. We're seeing the end. Okay, what is a solution? A homogeneous mixture. Remember, homo means same. So it's a mixture that looks the same. Solute. A lot of people are getting solute and solvent mixed up. Solute is what is being dissolved. It is the smaller part of the solution. Solvent is what does the dissolving. It's usually water or a liquid, and it's going to be the majority of our solution. And that's kind of the pie chart for that. Okay, so when we're looking at solutions, we want to think, or like solutes, adding solutes to solvents, we want to think like dissolves like. Okay, so polar solvents can dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. Polar solvents dissolve ionic solutes, and that is because of charges. Remember that ions have an electron. One element took an electron from another, and then they have those opposite charges, and that's why they're together, because opposite charges attract. Okay, and so say we have water, which is our most common polar solvent, the universal solvent, that has a partial positive and negative charge because the electron is pulled a little bit to one side. So it's a little bit more negative on one side, a little bit more positive on one side. That's what polarity is. So because of, sorry, my dogs are barking. Hey. So because of that, it does have that kind of positive and negative attraction to ionic compounds. So when you have an ionic solute, a polar solvent will be able to get attracted to it and pull those pieces of it out, okay? We talked about water, dissolving. Electrolytes. Remember that if we dissolve a salt or something ionic, we're going to end up having those free electrons floating around in the solution, so it can conduct electricity, just like the free electrons in metal can conduct electricity. All right, let's talk about solubility. Solubility is the amount of substance that can be dissolved under certain conditions. So in this case, the solute is at the beginning. This is the solvent, and this is the temperature. So when you're looking at a graph, I will get to the graph. Well, let's talk about saturation real quick. Okay, so saturation, we've reached the max amount of solute that can go into that solution at whatever temperature we're at, okay? Whatever that situation is. We can't add any more unless we increase the temperature. And obviously, you have to increase the temperature and add more solute. Otherwise, you're just increasing the temperature. So let's look at, I guess let me define these things and then I'll go to the graph. Okay, supersaturated. Okay, so when we have more solute in a solution than can usually be dissolved by the solvent in that. And how do we get there? We actually have to increase the temperature, add the solute until we get to the point of solubility at that temperature, and then cool the solution down, and it will still be at the same amount of grams of solute in that amount of, 100 grams of water or whatever. So you have to get it supersaturated, you have to increase the temperature, increase the amount of solute, and then decrease the temperature of the whole solution. Now, unsaturated is basically you haven't added enough solute to reach the point of saturation. So unsaturated is like a sponge that you can add more, okay? Okay, looking at this graph, you're gonna want to know these graphs and read. Always read the X and Y axis, please. My voice is getting like scratchy from talking so fast. Okay, so this line is the line of saturation. Above the line, super saturated. Superman is, consider this like the skyline. Superman's flying up there. Super saturation. Okay, and then below the line is unsaturated. So we got more room. Okay. So you kind of want to read X and Y axes when we're talking about solute graphs. And I went through some examples for this in the other video where I talk about the review, and I will also have this on the review for the semester. So I'm not going to worry about it right now. Remember, if you're changing the amount of solvent or water, you have to keep the ratio still the same. So you have to change the amount of solute as well, because otherwise it will just sit at the bottom. Miscibility is liquids being able to, mix together. I don't think we really need to go into that too much. Acids and bases. Okay, acids donate hydrogen ions. So examples of acids are going to be like citrus, vinegar, and soda, and they're going to be like sour and corrosive. Bases are donating hydroxide ions. They're going to be slippery and bitter. Examples of that are going to be like household cleaners like bleach, soap, things like that. They can cancel each other out. We don't really have to worry too much about titration and things like that for this class. So remember the pH scale goes from 0 to 14. The middle is neutral. The lower numbers are acidic. The higher numbers are basic or alkaline. We talked about electrolytes already. Acids and bases can also be dissolved and make electrolyte solutions because they donate those ions. You can use testing for indicators. Do I want to talk about dissolving gases? I mean, okay, when you think about dissolving gases, think about the opposite of what you think about when you dissolve solids. So the temperature Gas will dissolve better at lower temperatures without being mixed and with more pressure. Okay, so pretty kind of the opposite of solids. All right, last unit. Here we go. Quick. Sorry, I didn't rewind my VHS before we got here. Okay, so indicators of a chemical reaction. Gas, precipitate, which is the solid at the bottom, or the like kind of cloudy look, right? Light, sound, temperature, smell or odor, color change, and a change in pH. And I should have cut this down. Okay, chemical equation. So we've been doing chemical equations for a few weeks now. Shorthand method, looking at what we're doing, okay? So we have the coefficient. So the coefficient is going to be the number of units of each substance taking part in the reaction. So that's going to apply to the entire compound here. So this 2 goes to both, okay? Remember. Chemical symbol. We talked about the periodic table already. You know what a chemical symbol is. State of matter. We have solid, liquid, gas, and aqueous, which is something that's dissolved in water. They're going to be in parentheses outside. It's just telling you what it is. Not really relevant to when we're talking about balancing equations and things like that. Subscript, okay, underneath to the right, little tiny symbol, tells you how many atoms of that element, not the compound, are in the unit, okay? So we cannot change subscripts. We can only change coefficients. Coefficients apply to the entire compound. The subscript only applies to this specific atom, unless it's outside of parentheses. Don't forget that. What's next? Okay, remember that potential energy is stored in bonds. Reactions occur, something really important to remember, reactions occur from making and breaking bonds. Like, that's a simple question you'll probably get on a test. It's like, what's happening in a chemical reaction? We're making and breaking bonds. We're releasing energy. So breaking bonds takes energy to do. They want to stay together. And forming bonds is going to release energy. So when we're talking about exothermic and endothermic, if you look on the product side or the right side of the yield arrow and you see energy, that is exothermic. It's releasing energy. That means less energy was required to break the original bonds on the left side of the yield arrow, and more energy was released when the new bonds were formed. Okay. Endothermic reaction, more energy is required to break the original bonds on the left side of the yield arrow, the reactant side, and then the new bonds are formed and less energy is released, or energy is absorbed. So you're going to have a drop in temperature versus exothermic, where you're going to experience an increase in temperature. Okay, and then you'll see, if you're looking at the equation, you will see the energy on the left side of the equation. Okay, last couple things. I went through a few examples of this with the review, so I'm not going to go too deep. Mass cannot be created or destroyed, just as energy cannot be created or destroyed. It only changes around, right? Mass is counting the amount of matter in an object, and remember that matter is atoms. This that I need to read? No. Okay, so when we're talking about a chemical equation and we're looking at conservation of mass, add up the grams on both sides of the equation and solve for x. That's all it is. 5 grams plus 12 grams equals 6 grams plus x grams of hydrogen. Okay, solve for x. That's all you have to do. It's basic algebra. You can do it. I promise you. You're gonna kill these questions. If you see a question that is a formula asking for you to basically balance the formula, and it's asking you like what what does this, represent or whatever? Conservation of mass is the answer. Okay, so having like a balanced equation is following conservation of mass theory. Okay. Balancing equations. Make sure you're counting the atoms on both sides. Don't let a tricky, spare oxygen over here with this water really get to you. It's if you don't count that water, you're gonna get tripped up. So counting, put the atoms in the middle, and then count on the left side, count on the right side, and then make them equal. Some of them are a little tricky. Takes a little practice. I promise you'll be okay. Make sure you're multiplying your coefficients by your subscripts, okay? And this subscript applies to both the oxygen and the hydrogen in this parentheses. Keep that in mind. Okay, I'm done. I said I was going to keep it under 15 minutes, and I tried, but it's 30 instead. Hey! And my dogs are freaking out, so that's my time to go. Please read your questions carefully. Please study. Please, please, please study. And you're going to kill it. Okay. If you want me to go over anything in more detail, just leave a comment. Okay. Bye.